Today in class we talked about simplifying radicals, and they were somewhat unusual compared to what you may be used to in that they all contain variable expressions. So you may wonder, why are we even bothering to talk about radicals in the polynomials unit? Well, you'll start to see as we continue on talking about radicals that there's a relationship between radicals that are conjugates and also polynomials. So let's just go ahead and get started with some review, and then we'll tie into the relationship with polynomials by the end of the lesson. Okay, so just a quick review. We have n. In terms of all of the notation, this little space here, which today in class we looked at square roots, cubed roots, fifth roots. This is what we call the index, and that tells you which root you're finding. Underneath the radical, we said this is called the radicand. And then, of course, this is our radical sign. Okay, so let's go ahead and start right in with an example. And this example is similar to number 1 from the back of today's classwork. So we have the square root of 50 minus the square root of 18 plus the square root of 8. And the directions are to combine and express in simplest radical form. Okay, and today we talked about which of the 9 expressions could be combined, and we said that they had to have like radicals in order to be combined. So in the form that these are each in, they wouldn't be able to be combined because their radicands aren't alike. Okay, so the first step is that we're going to go ahead and start to simplify them into perfect square parts. Okay, and you can, if you want, show the intermediate step, this step that I'm showing here in purple, but if you want, you can go right to the simplified form if you feel comfortable doing so. So for each of these, they're divisible by 2, and we said today it's a good idea to divide by a prime number, which often helps you to find the largest perfect square. Okay, so in this case 2 is prime. The next one that you would check if 2 didn't work would be 3, and then 5, and then ironically you would check 6. Even though 6 is not a prime number, its 2 factors, 2 and 3, are prime. And then you may even check 10, which is also made up of 2 prime factors, 2 and 5. Okay, so you can go right to, if you wish, to the next step, which would be the simplified form, 5 radical 2 minus 3 radical 2 plus 2 radical 2. So the square root of 9 is 3 because it has 2 identical or equal factors. Once you have all like radicals, you can go ahead and just combine your coefficients, including their signs. So we have 5 minus 3 and then plus 2. So we have overall 4 radical 2. And again, you can go ahead and check these using the calculator. So we would just type in radical 50 minus radical 18 plus radical 8 and double check that 4 radical 2 is equal to that. Okay, our next example is going to be multiplication of radicals. And again, these should be reviewed. So example 2, we have radical 2 times radical 3 minus radical 2. Okay, so as if we were multiplying polynomials, we're going to use and apply the distributive property. So we have the square root of 2 times 3 minus the square root of 2 times 2. So we multiply what's under the radical. And again, you can skip that purple middle step if you want and go straight to the next step, which is radical 6 minus radical 4. And again, if you wanted, if you recognize that this is just a radical times itself is equal to the radicand. So we have radical 6 minus 2, or negative 2 plus radical 6. Either way could be expressed. Okay. You can leave radical 6 like this. A common mistake that people like to make is to break 6 down into its factors, but it doesn't have any perfect square factors. It would just have its 2 prime factors, 2 and 3, so it wouldn't be helpful if we were to simplify it further. Okay, and then one last example for this section, which is dealing with rationalizing denominators. Okay, so we're going to start with the square root of 3 over the square root of 8. So we can never have a radical in the denominator, and so in order to deal with that, what we would want to do is to rationalize it, meaning create a value in the denominator that is not a radical. Okay? And there's a couple of different options for dealing with this. You could simplify the radical first. You could multiply it by something that will make it a perfect square. Okay? In this particular case, radical 8 isn't a perfect square. But if we multiplied it by radical 2, then it could be radical 16, and radical 16, of course, is a perfect square. Now notice I'm multiplying both the numerator and the denominator by radical 2 over radical 2, which means I'm multiplying essentially by 1. Okay, and so I haven't changed my initial expression. So now I have in the numerator radical 6 over radical 16. And again, if you want, you could skip right down to the final result, radical 6 over 4. Just make sure that you're cautious about your simplifying. Okay, the next thing I want to discuss is conjugates, because I did say that radicals are related to polynomials in some way, and one of those ways is with what we call a conjugate. So an example of conjugate radicals would be something like radical 3 plus radical 2 and radical 3 minus radical 2. Those would be conjugates. And the reason that we would call these conjugates is that, or an identifying characteristic, is that they have the same first terms, the same last terms. The only thing that's different is this sign between, or the operation, if you will. Okay, so we have plus versus minus. These two are conjugates. Where have we seen conjugates before? Well, we've seen them when we have something like x plus 2, x minus 2. Okay, x plus 2 and x minus 2, these are conjugates, or a conjugate pair, if you will. And what happens when we multiply these two? The difference of perfect squares. Those middle terms will cancel. And so once we multiply them, we are left with x squared minus 4. Okay. All right, I'm going to ask you for homework, and in preparation for tomorrow's class, I would like you to go ahead and multiply these two conjugates. Okay, so homework, multiply radical 3 plus radical 2 times radical 3 minus radical 2, and express your answer in simplest radical form. Be cautious and aware of the fact that a radical times itself is the radicand. You can multiply this either using distribution, or you could use the box method, whatever is comfortable for you. Okay, so that's the first one. And then the second one I'd like you to multiply is x plus y and x minus y. And then I'd like you to tell me what you notice that's similar about the multiplication of those two conjugate pairs. All right, see you all tomorrow.